So this is a shorter video, one on an incredibly important and centrally used technique in organic analysis. And it's used to understand what a molecule is, whether it is what we think it is. Now, there's a lot of ways to do that. And NMR is, of course, the most famous and most common. But mass spec cannot be underestimated as a really practical tool. It tells us a host more things than just the mass of a particle. So there are a number of different types of mass spectroscopy that are used in the modern world. There's one called time of flight. We'll talk about that, and one's using lasers and all kinds of things. But let's stick to the simplest one, the first one that was really understood, because if you understand all the aspects of this mass spectroscopy, then you can expand that knowledge to other types of MALDI-TOF and things like that, so that you're conversant with mass spec. So the first thing I want you to understand is contained on this first slide of mass spec. And I want you to go and look at this slide, but I'm going to go to a whiteboard and tell you what it says, because there's a simple idea contained in this. And that is that this ultimately tells you the mass of particles. So how does it do? Well, once you inject it into the machine, there are 5 steps. First, your particles are vaporized, because these need to be in the gas phase to fly as they will through this machine. Next, they're ionized. All right, so what happens is, what you have to picture is an electron beam is perpendicular to the path of your ionized material. It's already started down this path due to it's entered into this chamber, and then it's going to be spit out. What the electron beam, or we used to call it, get this, an electron gun. What the electron beam does is it knocks off an electron. So if your molecule enters here, what it is existent here is a molecule with a plus charge. Where does it knock it off? It really doesn't matter. As long as any molecule that loses an electron will be positively charged. Now, once you've got it in this, it's now positively charged. Now, what you do is you accelerate it down a vacuum tube. Obviously, to the extent you can create a vacuum is perfect, because you don't want your particles flying down there and being slowed or deflected or diffracted or interfered with by particles in there, oxygens or carbon dioxides or waters or whatever is in there. You don't want that interfering. So it accelerates down a vacuum tube. What exists here is magnets. What happens there is that it encounters those magnets and it deflects. So the particle M comes down here and it deflects through a magnet. Now, why is that important? Well, the reason that is important is like if you're in a small car and you take a sharp turn. It's not so bad, right? But if you're in a big car or a truck, that is a much more difficult assignment. Traveling at the same speed, light particles will deflect more. Heavy particles, simply due to the physics of inertia, won't deflect as much. So you're separating particles by their mass. Pretty exciting, right? And then the last logical step is you have a detector detection. And I like to think of this as often a phosphorescent thing, and that hits and that hits and that hits there. What you do is you assign these masses, right? So that's 100, and that's 110, and I know what that is, and I know what that is, and I know what that is. And I can adjust my detector, obviously, to be at the right range of masses for what I think my particle is. And I can get very, very detailed information about the mass. I've used something called high resolution mass spec, in which you can tell the difference between carbon dioxide, which I think is 43.9 something, and what was I going to say? C3H8, propane, which is 44.1. You can easily tell those apart. So that is the big idea. Now, looking back at our image, now that we have that information, here you are. And the first thing, you have a heater, vaporize it. Step one, vaporization. Two, it's ionized. Ionization is the second step. In the third step, what it calls for, it's accelerated through this vacuum tube. And in step four, what I call step four, it's deflected through a magnet, so that step five, it hits a detector. Now, that's incredibly powerful. Even if that was all you got out of it, that would be really powerful. However, you get a lot more from mass spec, because our electron gun can have a different consequence. If you ramp up the electron gun, you could take your molecule and smash it into bits, right? So we'll call it M1 and M2, 2 bits. Now, originally our M, which we'll call M1 and M2, were connected by 2 electrons in between them. And what happened is one electron is knocked out of the particle. So now what you have is M1 with 1 electron between them. And when they come apart, what you have is the one lone electron having to go to either M1 or M2. When the 2 fractions come apart, 1 electron is gone, so that one gets the electron and one doesn't. The one that gets the electron is uncharged. The one that doesn't gets the positive charge, right? So a covalent bond is each atom's bringing 1 electron. If one gets knocked out and this one keeps 1, this is remaining uncharged, whereas the other one that lost the electron is positively charged. So you could get 2 results. You could get, obviously, the opposite result. In other words, if you had a particle, let's say it's hexane, and it splits to CH3 and the pentane, you could have one of two results. You could either have the plus charge there, in which case it would have a mass of 15, right? Or that could be uncharged, and this would have a mass of whatever, the 60 and whatever. You'd think I'd be good at this, 72. And so on our mass spec, which gives us masses, there's 15, because this is 20, 40, 60, 80. And there's 72. We get both peaks. And obviously, we get C6H14, which is 7284. We get a peak there. And that is the peak of the charged particle itself, which we're going to call the molecular ion peak. And that should be intuitive, right? The peak that is the molecule is the molecular ion peak. So you can see how from a fractionization, from a fraction pattern, if you smash this thing into little pieces, it's not hard to do some detective work and get all the information about the molecule. Even if the molecular ion peak doesn't tell you everything you want to know, maybe some of the particles will give you enough information to get that. So a couple of things. Let's say this is the molecular ion peak, but this one is taller. Some fraction of it broke off and is more abundant. Now, if we're going to do this, we said that the x-axis is the mass. We should talk about, oh, by the way, the tallest peak is called the base peak. So molecular ion peak, base peak. Sometimes, very often, if you have a low enough energetic electron gun, you can only get the molecular ion peak, so it's also your base peak. Now, thing to know, this is a histogram. So what it tells you is the number of times that the detector was hit here, here, and here. Sometimes it would be mostly this one fraction, or mostly that fraction, or mostly the molecular ion. Tells you the number of times each peak hit it. In other words, it is what's known as a histogram, meaning it's kind of like a bar graph. It tells you how many of each number. So this is only a relativistic statement. We can't tell absolute truths about it. So we call this y-axis the relative abundance. How much of each one is showing up? Relatively speaking, there's a lot of that fraction and a little of the molecular ion peak, and there's some of that and some of that. Now, the x-axis, you would think it's mass, right? But here's the interesting thing. You have to get your head around. Let's say your molecule goes into the ion gun and it gets an electron knocked off. But as it's traveling through, it gets another electron knocked off. Now it's doubly charged. What comes out into that accelerating vacuum is M2 plus. It's lost 2 electrons. Now, as it heads towards these magnets, when it's accelerating, it's got twice the charge and it's twice as attracted, so it's being pulled twice as fast. In other words, it's not just mass that matters, and it will deflect twice as hard. it's also charge. It's mass that matters, right? It'll deflect relative to its mass, and it'll deflect more, meaning sharper around that current curve, depending on its charge. So as charge goes up, mass goes down. In fact, it's mass over charge. In other words, the x-axis, which you think it would be mass, is not. It's the amount of mass over the amount of charge. And how that looks on a typical MS is M over Z. So let's hypothetically say this is 80. We fully expect a peak to exist here. Maybe it's small, maybe it's big at 40. Now, that could be a fraction, or it could be the M2 plus, the doubly ionized peak. You have to be aware of that. That's really important. So now that we know these things, we can go back and look at that PowerPoint that's in your possession, and we can look through these ideas and understand what they're saying a little bit better. And so by going through this, I'll be reiterating what I said. So you can get two things. Well, first of all, you can doubly ionize. You could triply ionize, in which case the mass would be 1/3, but typically you don't see more than the mass or the mass in 1/2. So M over Z, right? Y-axis, relative abundance. It's a histogram, right? So, and you just know on the second exam, I'm going to have mass spec, and I'm going to ask you, what's the y-axis, what's the x-axis? And I'll only accept the correct answer of y is relative abundance and x is M over Z, or mass over charge. Anything else won't get credit. Notice that the peak at 57 here is called the base peak because it's the biggest, and that the M plus, the furthest to the right, the biggest mass, is the molecular ion peak. It's the unfragmented peak. It's the peak molecule in its entirety with a +1 charge. This molecule, hexane, has a mass of 86. And so if you knock off one peak, one methyl, you would get 86 minus 15 is 71. Oh, look, there's a 71. Or 71, because it got charged and the methyl bit had the single electron, or the 71 got the electron and the methyl got the positive charge, and you would expect 71 and 15, and there they are, the two fragments. Or you could knock off CH3, CH2, and then you'd have a mass of 29. Or you could knock off a propyl, and you'd have a mass. You can see what's going on. Now, what are these littler peaks? What are these side peaks? Well, obviously, our atom isn't pure in the sense of isotopic purity. If there are isotopes, they will have an extra neutron or not have as many neutrons. You might have carbon 11 or carbon 13 or carbon 14, and you would get peaks representing those other possibilities. In some cases, these are signatures you can actually understand. So here they are talking about how you can have one piece be positive, the other an ion, or the first piece be an ion and the other be a radical, frankly, is the term for it. So here we're talking about the +2. It would have a mass of 43 in this case, because it would have +2 as a charge, and it's mass over charge. Oh no, the M+1, sorry, is one extra isotopic mass. Here's a really famous example of how mass spec can give you information, based on 2 isotopes. Now, the thing about bromine is it's got 2 isotopes. Now, in the periodic table, it's got a mass of 8. But did you know there's relatively little, effectively 0, bromine with a mass of 80? It's like 50-50, 79 and 81, which is amazing, isn't it? So the mass on the periodic table doesn't tell you about the mass of the particle itself. So there's the base peak is at 77, because it's C6H5. And there's a small peak at 50, which I would have to think about. But the whole molecular ion peak is at 1, whatever it is, 59. And so, or 158, 156. So you can see that from the ions or the isotopes that might occur, you might tell more than just, you can get information you wouldn't have otherwise. Chlorine might be 3 to 1, because it's 3 to 1, 35 to 37 isotopic ratio. So that's really powerful in mass spec as well. And really, amazingly, what you need to do is practice with a lot of mass spec examples, which I'll try to provide for you. In fact, I'll have some videos on mass spec that I hope will flesh this out. And I'll create some example problems eventually that will go in our practice problems folder somewhere below here. So really, that's mass spec, and it's an incredibly powerful tool. If you're taking 252, we have mass spec up in the lab that, like all the equipment, we can't use unless I can get us all to create samples and put it on the carousel, because it has an auto sampler. At some point, I'd love you all to come see the exterior of the mass spec. It's tied to a gas chromatography unit, so it's GCMS, which is incredibly powerful. So anyway, thanks for this shortish video on mass spec.